I limit my options for the second method. Because the second method must go on carbon number 3, which is either 1, 2, 3 or 1, 2, 3. It is easier for me to draw it with the front carbon, doesn't really matter. So I'm going to put the methyl, carbon number 3, I'm going to put it here. Now, what I do know is that it's cis, so the other methyl must be pointing up. What cis means, cis has nothing to do with axial and equatorial. Cis just means that you're on the same side of the molecule. So if the two methyls are cis to each other, they must both be pointing up. Which means A1 is diax. My two methyl groups are axial to each other. Okay. When the ring flips, whatever was axial becomes equatorial. This carbon, the rightmost carbon, is here. Carbon was up, now the carbon is down. My methyl is now equatorial. But of course, it's still up. Above the horizontal, but ax goes to egg. On this carbon, which is here, what was axial becomes equatorial. So this methyl group is now here. So A2 is a di-equatorial conformation. And if I ask you to tell me the relative, to indicate the relative populations, you would say, look, what destabilizes the chain? Having my group axial. Having two of them axial, well, that's pretty bad, because now, right, having two of the groups in the axial position, flip the chair, right, having two of the groups in the axial position, stay, is bad because now the 1,3 diaxial interaction that destabilizes the chair has two large methyls bumping into each other. That is a significant amount of steric discomfort. Which means the propensity for the molecule to rotate out of the 1,3 diaxial arrangement, the diaxial arrangement, is going to be huge. So I'll have my equilibrium will lie very far to the side of the 1,2 diequatorial. Okay, I don't need numbers. I just need to know it will prefer this one significantly. What about B? Well, B is the trans compound. So I'm going to pick the top right position as my methyl, my position in the far right. I'm locked into carbon number 3 now, so it's 1, 2, 3, or 1, 2, 3. I like the front carbon, you can pick the back carbon, it doesn't matter. But if the groups are trans, if this is up, then the other methyl must be down. And down where? Well, look, this carbon has two exocyclic bonds. There is an up axial and a down equatorial. So I'm going to use the down equatorial, which puts my methyl here. This is an ax-ec conformation. One axial group, one equatorial group. When the ring flips, whatever was axial becomes equatorial. Whatever was equatorial becomes axial. This is an ax-ec conformation. Well, it's the same groups, axial and equatorial, which means the instability here is exactly the same as the instability in the conformation. So the energies of B1 and B2 should be the same. So I've drawn my four conformers, indicated by the position of equilibrium, what are the relative densities, population densities. If I ask you to rank them now in terms of energy, well, the most energetic is the diaxial, followed by B1 and B2, which are degenerate, followed by A2, which is the most stable. And of course, if I asked you for stability, then it would be exactly the opposite, right? A2 would be at the top, B1 and B2 would be in the middle, and then A1 would be the least stable. So that's the typical form that these will take. What if I ask you to do this for, oh yes, actually, that's good, that's good. Okay, I'll come back to this in a second. What if I ask you to do this for, say methyl? So the cis 1,4 dimethyl and the trans 1,4 dimethyl. Okay? How would they differ? I want to come back to this. I'm going to leave this on the board. So I would draw the chairs. Let's call this one C and D. What are the substructures for C? Well, I'm going to draw both chairs. One chair, two chairs. And then I'm going to call it C1 and C2. And then I'll draw D1 and D2. The cis, I happen to like to start here. Cis means they're the same side, so for carbon number 4, I'm going to be here. So that's my axial. Because they have to be the same side, this will be equatorial. So they're both pointing up. This is an ax-ec conform. When the ring flips, axial becomes equatorial, equatorial becomes axial, what goes up remains up, and this is also an ax-ec conform. So these should be degenerate. In the trans, this will point up, this will point down. So this is the diax, and as we imagine when the ring flips, the diax becomes a diec. And in this case, then, I have more of D2 than I have of D1. And in terms of increasing energy, D1 is the most energetic, D2 is the least, and C1 and C2 are equiangelic, or degenerate. Okay? What would happen if these two groups are not the same? What if I had a methyl and an ethyl? If I had a methyl and an ethyl. So let's put the ethyl here, methyl here. When the ring flips, ethyl and methyl. Now when they were both methyls, or for that matter, they're both ethyls, they will be degenerate. But in C1, in this new version, in C1, my ethyl group, the larger group, is axial. Which means there are more severe 1,3 diaxial interactions between ethyl and H, because the ethyl is bigger, than in the diaxial interactions between methyl and H. Because the methyl group is smaller, right? Because the methyl group is smaller, its interaction with the H's isn't quite as severe as with the larger ethyl group. Which means the need for this to be equatorial is greater than the need for that to be equatorial. In which case the system shifts so that more of C exists as C2. So you can hide the larger ethyl group in the equatorial position, where there are no 1,3 diaxial interactions involving the ethyl, and that ethyl is staggered to its neighbors. So that breaks the symmetry when I've got ethyl and methyl. And if I have ethyl and methyl, right? And then ethyl and methyl, well again, clearly the diaxial is still the worst, although it would have moved this way. The diequatorial is still the least energetic. And now C1 and C2 are no longer degenerate. It turns out in this case, C2 is more stable than C1. So that would be the relative energies of your set. So you see where this is going. Based upon the sizes of the groups and where the groups are, this is why it's steric, based upon size and location, we can make a judgment call as to the relative energies of the individual conformers. And of course, when you get to one where you've got like a T-butyl group, the T-butyl must be equatorial. And therefore you have 100% with the arrow going towards the equatorial T-butyl. But an interesting thing happens in this question. In the particular case of the cis 1,3 diaxial, yeah, let's do it this way. Yes, let's do this way. So we're going to look at 3 different cis 1,3 diaxial species. And we're going to change these things to Z. So Z is some group that we have. And again, our conformers are going to be, so I'm going to have Z, and I'm going to have percent of A1 well, really, that's all I need. It's just percent of A1. So percent of A1. Because obviously, it'll be 100 minus whatever this number is for percent of A2, right? So percent of A2. So when Z is H, and then we'll pick methyl, and then we'll pick chlorine, and then pick OH. I'm going to pick fluorine. So when Z is H, right, so I've got H and H, what is my fraction, my percentage of A1 and A2? Well, when the H's, there's no meaningful 1,3 diaxial interaction. My groups are exactly the same as all the other H's in the molecule. So I'll have 50% of this one, 50% of that one. That's the standard chair, the standard cyclohexane, right? It's a standard cyclohexane with no groups at all, no substituents on the molecule. So the 2 chairs, this one and that one, are degenerate. So it's 50-50. When I've got methyl, there is significant 1,3 diaxial interaction here. Now there's also interaction with the H. So this methyl interacts with the H, that methyl interacts with the H. Right? So that interaction is destabilizing. And the system is going to try to rotate out of it, it's going to ring flip, to give you more of the diequatorial than the diaxial. And I might get, I don't know, let's say only 25% of this one, and 75% of that. And that would be reasonable. What if I made them fluorines? Now, fluorine is a little bit smaller, well, fluorine is smaller than methyl. And I thought of using fluorine. I could do the same thing with chlorine as well. Chlorine is a bit bigger, but it's fine. Fluorine is smaller than methyl. And if I had 2 fluorines, so fluorine is a little bit smaller than methyl. If I had the 2 fluorines, my steric interaction would be a little bit less. Okay? If I had chlorine, it'd be a little bit worse, because chlorine is bigger than methyl. So where would I expect it to be with the fluorines? Well, the steric interaction would be less with the fluorines. And if it was only steric, I might have expected maybe 30 to 35%. But in reality, I'd probably get close to and 10%, right, and 90% here. Well, why is that? Well, the fluorines are strongly electronegative, which means there's a negative dipole on those two fluorines. So that's superimposed upon the steric interaction, there is now an electronic interaction. And that severely destabilizes the system. Right? Repulsion is destabilizing. So this is going to fold by both electronic and steric repulsion out of the diaxial into the equatorial. So I will have very little of the di-equatorial, that of the diaxial. Well, what if I had OH? So the OH group is a little bit bigger than fluorine. It's a little bit smaller than methyl. So I might have expected it based upon steric factors. Sort of somewhere in the middle maybe. Plus, because the O is electronegative, I might have expected, because it's slightly bigger than the F, in fact, really, because it's slightly bigger than the F and O is electronegative, I might think of the number being somewhere even less than 10. Turns out, if I do this, it's usually somewhere around 45 to 55. Or darn close, 45, maybe 50-50, somewhere in that ballpark. But a lot higher than I'd expect based upon size, which should not help me, and electronegativity or repulsion, which should not help me either. So why is it that we're getting so much of of what should have been the less stable diaxial? Well, it turns out that if I had OH, something interesting happens. You get hydrogen bonding. And you get hydrogen bonding in a 6-membered ring. 1, 2, 3, 4, 5, 6. As you've seen, 6-membered rings are intrinsically stable. So hydrogen bonding actually stabilizes the 1,3 diaxial conformant. So what does this mean? It means the population densities of the cyclohexanes are dependent upon the marriage of steric factors and electronic factors. Either it's a simple matter of electrostatic repulsion, or as you can see here, hydrogen bonding. So you really want to judge each case based upon the merits. As a rule of thumb, the large group, or the larger group, or the largest group, if you have more than 2 substituents in the ring, the largest group wants to occupy the equatorial position. But you want to look at the impact of not just steric factors, but electronic factors as well in determining the relative stabilities of these groups. Okay, so at this point we will stop. That will end our lectures on Module 5, and I will post for you guys as well lectures on Module 6. Okay.